What is the perfect gas law? Let's take a container which contains some gas and let's see what we can do with this container. If we take the container and we try and squish it, then we will discover that it changes shape, like, probably not like that, but something like that, and we will find that we can increase the pressure inside by squashing it, and we can feel that pressure as a force. And we know that that is because the particles of gas become close together, and as they collide, they hit the sides of the container. The closer they are, the closer we've squashed them, the more of those collisions we get, and therefore the more force is exerted on the outside of the container. And this is something that Robert Boyle discovered in the 1600s, I think it was, which has become known as Boyle's law, which is that pressure is inversely proportional to volume. Basically, what that means is that if I squash my container down, I'm going to get a smaller volume, and therefore I'm going to get a larger pressure. Okay, and the opposite is true. If I increase the volume that I've got of my container, which the gas is contained in, then I will decrease the pressure, and we can see that relationship in this equation here. What else can we do with this balloon then? We can heat it up or cool it down, and if we heat it up, we give the particles more energy. We know that causes them to move around faster, and therefore if I don't change the size of my balloon, it will give me a higher pressure, but actually because the balloon has got flexible edges, it's probably just going to expand. It will give me a bigger volume. And Jacques Charles was someone who did a lot of experiments on this with gases by changing their temperature and measuring their volume. He was able to come up with something which in this form is recognisable as Charles' law, which is that if you keep the pressure constant and you end up with a volume equaling some sort of constant number times the temperature, and also because pressure and volume are related by Boyle's law, we can also write that if we keep a constant volume, then the pressure is equal to a constant multiplied by the temperature. One of the things that you can do with Charles' law is you can see that you can plot it into this form, y equals mx plus c. There's no plus c, obviously, so it's just mx, and we can see that our constant is equal to the gradient if we plot the volume on the y-axis and the temperature on the x-axis. And if we do that, we end up with this graph here, which Jacques Charles was able to predict that there was a temperature at which the volume of gas would basically be nothing, and there can't be anything colder than that. And so this is one of the experiments which initially set the idea of an absolute zero. Working on that, we ended up with a couple of decades later with the Kelvin scale, where this minus 273.15 is actually set as 0. And for that reason, when we're talking about the perfect gas law, we always have our temperature where that point there is set to 0. We always use the Kelvin scale of temperature, and that's going to be important later. So the last thing I can do with my balloon is I can add more gas, and there are two ways that this could go. Either if I keep my container rigid, if it's a solid balloon which doesn't expand, we're going to increase the pressure, or more likely if the container is flexible, increasing the number of particles is going to increase the volume. And this is basically Avogadro's principle in mathematical form. We could write it as something like this: the pressure equals a constant times the number of gas molecules in there. So Avogadro, having done some work on this relationship as well, we have a set of equations that we can combine. So hopefully you can see the equations that we've got down the side here we can combine. You see we have very similar things here. If we, on this side of P, we've got V here as well, we could actually take that V out from under this fraction, multiply both sides by V, we'd end up with PV on this side as well. So we're going to start with PV there, and then we can see that N and T sits on this side of the equation. We can rewrite this as PV equals some sort of constant that combines all of these things together, multiplied by the number of moles of gas times the temperature. And if we were to give that constant a letter, which we do when we call it R, for the gas constant, we would find a form of the equation like that. And because this is a, if I put this form up again, we can see that this takes the form y PV equals mx, which is the constant times nt. If we were to plot this on the x-axis and this on the y-axis, we should get a straight line graph with this gradient. And we do, for pretty much every gas, as long as it's at a very low pressure. And this rule is a great rule for predicting the volumes and pressures and how they're related of gases within a set of limitations. And this is the first step towards understanding the behaviour of gases. Now, obviously, there are some limitations to this model. For example, the big one is that it doesn't really take into account the size of the molecules or the intermolecular forces. But generally speaking, at low pressures, it is a good approximation, if nothing else. Now, I said earlier that the unit was going to be really important, and that we were using Kelvin here. And that's because the value of R actually changes depending on what you're using. So pressure could be measured in atmospheres, or it could be measured in torr, or it could be measured in pascals. Volume could be measured in decimeters cubed or meters cubed, and depending on what we put into our equation here, we're going to get a different value out for R. And so for A-level chemistry, we are going to use for pressure, pascals, and we're going to use for volume, meters cubed, and for number of moles we're going to use moles, unsurprisingly, and for temperature we're going to use Kelvin. And the reason for that is that we end up with a value for R which is in joules per Kelvin per mole. And it works out because a pascal is a joule per meter cubed. We multiply that by meter cubed, we end up with joules, and then we end up with moles and Kelvin, obviously, on this side of the equation. So our gas constant R is given under those circumstances. It's actually on your data sheet as well as 8.314 joules mole to the minus 1, Kelvin to the minus 1. Depending where you see it, sometimes these are the other way around. So that is our perfect gas law. Now, despite its limitations, at A level, we will use this gas law to calculate number of moles of gas, as long as we know the temperature, pressure, and volume of that gas.